The adsorption selectivity is a commonly used metric for quantifying the separation efficacy of microporous crystalline adsorbents such as zeolites, metal organic frameworks, and zips. The adsorption selectivity is the ratio of the component molar loadings of 1 and 2 divided by the corresponding partial fugacities of components 1 and 2 in the bulk fluid phase mixture. The component molar loadings are each proportional to the mole fractions of the components in the adsorbed mixture, X1 and X2, and similarly, the partial fugacities of the components 1 and 2 in the bulk fluid phase are a product of the mole fractions of the components in the bulk fluid mixture times the total fugacity of the bulk fluid phase F sub T. So the separation selectivity is also written as the ratio of the component mole fractions in the adsorbed mixture divided by the corresponding mole fractions in the bulk fluid phase mixture. My talk today is on selectivity reversals. There are basically two types of selectivity reversals that are encountered in practice, illustrated on the left side by the selectivity of 1-propanol to ethanol in chabazite, with increasing pore occupancy, the selectivity of 1-propanol to ethanol decreases to values below unity, and for pore occupancies greater than about 0.7, the adsorption selectivity is in favor of the smaller molecule ethanol. This selectivity decrease with increasing pore occupancy is due to entropic effects that favor the smaller molecule. Such selectivity reversals are anticipated by the ideal adsorbed solution theory. Indeed, the predictions of the ideal adsorbed solution theory based on the data on the unary isotherm is shown by the dashed lines. This is one class of selectivity reversals where entropic effects cause selectivity reversals at high pore occupancies, and such reversals are in favor of the smaller molecule that has the higher saturation capacity. Such selectivity reversals are anticipated by the ideal adsorbed solution theory. In a different class of selectivity reversals shown on the right hand side as an example is that experienced for mixtures of CO2 and ethylene in 5A zeolite at a temperature of 238 Kelvin. The red circles are the experimental data that is described in my ACS Omega paper. Here, the total occupancy is maintained nearly constant by maintaining the total pressure at 1.07 kilopascals and at a temperature of 238 Kelvin. the bulk fluid phase mixture composition is changed, and we plot here the mole fraction of CO2, which is component 1 in the adsorbed phase, that is X1, as a function of mole fraction of CO2 in the bulk gas phase mixture, which is Y1. And we note that at a bulk gas phase composition of CO2 of 0.7 approximately, the selectivity reversal occurs from being CO2 selective to being selective to ethene C2H4. And at this point we have Y1 equals X1, and that is the azeotrope composition. So selectivity reversals are also possible by changing the bulk gas phase mixture composition at constant pore occupancy or nearly constant pore occupancy. Such reversals in selectivity are not anticipated by the IAST. And the primary objective of this video presentation is to examine the reasons for the failure of the IAST and the elucidation of selectivity reversals and azeotropic adsorption. The background to the material I will be presenting is described in the two papers cited here. Watch also other video presentations on my YouTube channel. We summarize the key assumptions that are made in development of the IAST. All the adsorption sites within the microporous crystalline material are equally accessible to each of the gas molecules, and this implies there is a homogeneous distribution of gas adsorbates within the pore landscape. There is no segregation, no congregation, or preferential siting of gas molecules within the pore topology. And the specific surface area that is occupied by each molecule remains unchanged in mixture adsorption. Let us consider the example of adsorption of a mixtures of CO2 and propane in LTA4A zeolite. LTA4A consists of cages with a diameter of approximately 11 angstrom. Each cage is separated and connected to adjoining cages by narrow windows that are approximately 4 angstrom in size, hence the name LTA4A zeolite. This contains extra framework sodium cations indicated in blue that are located as shown here. Many of these cations hinder the intercage hopping of gas molecules by occasionally hovering around the window regions. For adsorption of mixtures of CO2 and propane, we have a inhomogeneous distribution of guest adsorbates within the pore landscape due to preferential locations of CO2 in the window regions, because CO2 can fit snugly at the windows, and it usually is present in higher concentrations near the window regions, as is evident from this computational snapshot. The propane molecules are too bulky to locate at the window regions and are primarily or predominantly located within the cages. In a scenario in which the composition of the mixture contains a very small amount of CO2 and a large proportion of C3H8, the CO2 is located almost exclusively in the window regions and faces relatively less competition with the propane molecules that are in the cage interiors. Therefore, at low mole fractions of CO2 in the bulk phase, the selectivity is in favor of CO2, because the CO2 does not face stiff competition because it is isolated and locates at the windows. With increasing proportion of CO2, it is necessary to have CO2 locate within the cage interiors, because the windows are all fully occupied. And within the cage interiors, the CO2 has to undergo competition with the propane molecules that have stronger adsorption strengths. And we note that for higher CO2 compositions in the bulk fluid mixture, the adsorption selectivity becomes increasingly in favor of the propane molecule. And we have the azeotrope composition at a mole fraction of about 0.1 for CO2. The selectivity reversals are predominantly or primarily caused due to inhomogeneous distribution of adsorbates within the pore landscape. Indeed, the deviation from the IAST is the reason for azeotrope formation and selectivity reversals. The IAST fails to anticipate selectivity reversals because the important assumption, or one of the important assumptions of the IAST, is that the guest adsorbates are homogeneously distributed within the pore landscape, and the competition is between the guest molecules does not depend on the composition of the bulk gas mixture. I show here data on water ethanol adsorption selectivity for mixtures of water and ethanol at a total bulk fluid pressure of 10 kilopascals and temperature of 300 Kelvin. And the selectivity is plotted as a function of mole fraction in the bulk fluid phase mixture Y1. The data is generated from configurational bias Monte Carlo simulations of water ethanol mixtures in Chabasite, shown here, which is a cage window structure with windows of approximately 3.7 angstrom. This is another cage structure, DDR, shown here by the blue triangles, where the window dimensions are approximately 3.6 to 3.7 angstrom. The red circles are the data for ZIF8 that has a crystallographic window aperture of 3.3 angstroms, but the windows are flexible, allowing even larger molecules to pass through. The cages are larger than those of DDR and Chabasite. We note that at very low compositions of water in the bulk fluid mixture, the selectivity is in favor of water. And with increasing composition of water in the bulk fluid mixture, the selectivity tends to reverse in favor of ethanol. The higher water ethanol selectivity at low compositions of water is due to molecular clustering caused by hydrogen bonding that results in enhanced water ingress into the microporous crystalline structures. Molecular clustering causes a violation of the tenet of the IAST that demands that that each gas molecule occupies the same surface area in the mixture as for the pure components. If molecular clustering occurs due to hydrogen bonding, the water ethanol cluster will occupy the same space as that of either water or ethanol on its own. And the IAST fails to predict selectivity reversals as the composition of water changes in all cases. The background details are provided in my paper published in ACS Omega in 2020.